Oh, well, welcome everyone to this talk. Obviously, I am not very experienced with giving seminars via Zoom or in fact in general, so we'll see how this goes. So I'll mostly be going through this PDF that I've written up, which hopefully you can all see on screen. Is it visible to everyone? Yeah, okay.
Yep.
And I really wasn't sure kind of what level to pitch the talk at, because I don't know how experienced any of you are with kind of elliptic curves and cryptography and anything like that. So apologies if it's a bit too basic, but hopefully we can get through it quickly if it is, and hopefully it's there's something in here which everyone can benefit from, except probably Lucas. So yeah, so it's a bit of a break from the kind of very theoretical number theory stuff, because obviously cryptography is a bit more of an application of number theory. And this follows on directly from what Tristan was talking about in the introductory kind of lecture thing the first week. So if you haven't seen that or read his notes, or if you aren't already familiar with kind of elliptic curves and things, then let me know now, or then I can do a bit more introduction, or go and read those notes or whatever. But I'll just quickly go over some of the stuff to start off with, and then yeah, get into some cryptography. So the first thing is obviously what an elliptic curve is. So hopefully everyone's seen this equation before. You've just got a curve like this, and it should be non-singular, which we saw is the same as the discriminant here being non-zero. So you have to just choose an A and a B such that this thing isn't zero, and then your curve is non-singular. And there's quite a difficult definition of elliptic curves over general fields and everything, and coming into some algebraic geometry and stuff. One thing to note is that it's got this genus 1 condition here, because I'll mention a little bit about hyperelliptic curves closer to the end of the talk, if there's enough time, just because that's been something that I've worked on a bit recently, and it could be interesting to some of you that have already seen lots of plain old elliptic curves before. But yeah, basically any curve like this, and we'll be working over finite fields only in this talk. So if I don't say explicitly what field the curve is over, it'll be just fq for some prime power q, that's p to the power of n. And we want to look at the group of points over fq rational points. So that means both the coordinates are from fq, and a and b are also from fq, as well as the point at infinity, which is that special point which acts as the identity for the group law. So yeah, one of the important things to note about elliptic curves is that they are basically, it is just a group, and the fact that it's a group is not just a coincidence. It's quite a deep idea, I guess, from algebraic geometry, that the elliptic curve is isomorphic to its Jacobian, which is where the group law actually comes from, or its class group of divisors. So the group law that you saw, the chord and tangent rule, which is that one where you draw a line through 2 points, and then the third point that it hits, you mirror that in the x-axis, and that's kind of the sum. That chord and tangent rule doesn't just come from anywhere. It's not just some rule that someone made up that kind of just worked. It does actually correspond exactly to the group law that you would get on the Jacobian, which is isomorphic to the elliptic curve. So it is all quite a deep theory, not just drawing some lines and you get some points and everything. But at the end of the day, for cryptography, none of that is super important anyway, because we just need a group. And one of the nice things about the group is that because you get kind of the same security, it turns out, for a lot smaller numbers than if you were using RSA and things. I'll get to all this in a minute more in depth. But basically it's a lot more like efficient because the numbers are smaller, and so that's where the real benefit comes from in classical elliptic curve cryptography. None of it really matters that it's a curve or whatever, it's just an efficient group that we can use for the cryptographic schemes that we'll see. So yeah, there's a bit of theory on elliptic curves and like the number of points in this group here, which is probably not super important for now. I just wrote it in here because I just spent the time writing this. So if you are interested, just have a look. Maybe there's some things in here which you want to ask questions about or whatever. But yeah, and there's this whole thing of like the torsion subgroups and everything, which I guess Tristan will come to in a couple of weeks' time when he's talking about two isogenies. So yeah, I'll leave that for now, and mostly focus on some of the like real applications of elliptic curves in cryptography to start with. So yeah. So yeah, just to quickly refresh, we saw the chord and tangent rule, where you can add 2 points on the curve and get a third point. And remember from Tristan's talk that was an associative and commutative operation. So, and the identity is the point at infinity. So yeah, we've got a nice group and it's a commutative group, and that's all you really need to even know. And then we can also define scalar multiplication of points. So this has nothing to do with multiplying the coordinates of the points by a number or anything. It's literally just repeated application of the chord and tangent rule. So if you want to calculate 2 times p, we'll write it in square brackets. Then it's just p added with p using the tangent at p. And so you just can like do that over and over again if this is 3 or 4 or 5, whatever. And that gives you scalar multiplication. So that's just kind of a shorthand way of writing the group operation that we'll use a bit later on. Yeah, and another thing to note is that the group of points on the curve is not necessarily cyclic, but in the cryptographic schemes we'll see below, we use always a cyclic subgroup. So we'll have a generator point, and we'll kind of just work in that cyclic subgroup, but that's not necessarily all the points on the curve. Usually the curves that people use in cryptographic schemes are, they have a low cofactor, this thing here, meaning that the total number of the FQ rational points on the curve divided by the order of the cyclic subgroup is quite small, maybe like 2 or 4. So it's still like a lot of the points, but it's not all of them. So yeah, that's kind of a refresher on elliptic curves. At any point, if anyone has questions or wants me to speed up or slow down or whatever, just message the Zoom thing or whatever, I guess. But yeah, so yeah, just a quick intro to hash functions as well, because yeah, I don't know how much crypto anyone's seen or just maths. So apologies if this is very basic and overly repeated, but we'll need what a hash function is later when we come to one of the signature schemes. So it's basically just a function which takes an input of any size, like it could be a number of like arbitrary size, or maybe sometimes you write it as a string, like a sentence or something. It can be any length, but the idea is that it always maps to a fixed length output. So common hash function is like, for example, SHA-256. So that always maps any size input to an output which is a fixed 256-bit size. And the properties that are important there are that it is deterministic, which means that if you calculate the hash of something and then calculate the hash of the same thing, you should always get the same output. It can't like randomly generate an output each time. But it should be, I've said like pseudo-random here, but it just means basically like the output kind of looks random. If you have 2 inputs, maybe like x and x plus 1, even though that they're related somehow, if they're only one number different or whatever, one bit different, if you hash them, you should get like entirely different output. They should look very unrelated. Thirdly, we've got pre-image and second pre-image resistance, which is basically just saying it's hard to invert it. It's not really inversion because obviously it's not, yeah, obviously it doesn't have like a well-defined inverse because it's not injective, because the input size is arbitrarily large, but the output is fixed size. So there's lots of different inputs that can map to the same output, but finding any of them should be hard. If you're given, if you want to say like, find me a number which hashes to 1, then that should be really hard to do. Pre-image and second pre-image are slightly different conditions. The second one is really saying, if I give you a number like h of x, find me a different value y such that h of y is equal to h of x. But they're kind of the same thing. Like, they're both talking about how you could find a input value which hashes to a specific output value. And then finally, collision resistance is just finding two different inputs, x and y, obviously not equal, such that their hash is equal. So those 4 things here are important properties for a cryptographic hash function. Sometimes you'll see like just hash functions used various places, and hash function by itself doesn't necessarily have to have some of these conditions like pre-image resistance, collision resistance, some of this stuff. But I think it just has to be deterministic. But for cryptography, these second to fourth properties are pretty important for the security and everything. So I've just kind of listed them there pretty informally. Does that make sense to everyone? If anyone's not happy with the idea of a hash function, just yeah, message or say something or whatever. But otherwise, I'll move on. So yeah. Yeah, so now I'll come to some, I've called it classical elliptic curve cryptography here because a lot of what Stephen's research group do now is what's known as post-quantum cryptography. So this is cryptographic schemes which, even if an attacker had a quantum computer, there's still no known way that they could break the scheme, that they could, for example, find the secret key or whatever. So, but I won't get into that first. I'll start with classical elliptic curve cryptography. And actually I'll leave the isogeny stuff completely because I think Tristan's going to talk about some 2 isogenies and things in a couple of weeks. So I'll leave that stuff completely for today. But yeah, that's why this classical is here, if that's confusing for anyone. Yeah, so typically, like in a textbook or something, if you were just looking at cryptography or whatever, one of the schemes you'll see quite a lot is RSA. And RSA has this, it's quite like an elegant scheme, I guess, with some cool number theory. So if you do a course in number theory, that one probably would come up quite often, or discrete maths or whatever. And its hardness, it's like security, is based on the difficulty of factoring a large number into its prime factors. So the idea is that if you have 2 big primes, P and Q, and multiply them together and get a big N, then if you give someone this big N, it's hard for them to find the factors P and Q. So that kind of assumption is what underlies the security of the scheme. And the idea is that if someone could factor them, then they could break the scheme. So that's how a security proof kind of works. And I won't cover RSA because I don't think it's very necessary today. If you are interested, there's lots of descriptions of how it works everywhere and lots of textbooks and online and everything. But the important thing is like the difference in hardness assumption that we'll be seeing today. So generally in cryptography, there's some exceptions when people come up with a scheme that doesn't have a security proof or whatever, but for kind of mathematical cryptography, a lot of the time it's pretty important to have what's called a security proof. So if you propose a scheme that says this is how we can encrypt something, or this is how we can create a signature from something. Pretty much everyone will like to see a proof that breaking that scheme is equivalent to solving some hard problem in maths. And that kind of gives people a bit of reassurance that the schemes might be safe to use. So that's what it means if we talk about like assumptions and hardness assumptions and security proofs and everything. And so with elliptic curves, the hard problem that's pretty much always used is the elliptic curve discrete logarithm problem. So the problem itself is that if we have an elliptic curve over a finite field, fq, and 2 points on the elliptic curve to find the value x such that x times p is equal to q. So obviously this is like a fairly informal description of the problem. And if you already knew, like p and q shouldn't be related. Obviously if q is equal to 2 times p, and then you say, oh, look, I've broken the discrete logarithm problem, that's obviously not what it's talking about. It's talking about like a random p and q or whatever you like. It's hard to find x. So the place where the name comes from, the fact that it says logarithm in the name, is that it's kind of similar to the normal logarithm, if you think about it. Because the normal logarithm of a number, like b to the power of c equals a, the whole idea is that if you're calculating the logarithm of a with the base b, that you get back c. So here we're looking at like what number you have to multiply p by to get q. So the log of q with base p is x. That's the discrete log problem. And yeah, the hardness assumption is that if the field size is really large, this fq, the q here, if it's like a 256-bit prime or prime power or whatever, then it's really hard to solve this problem in general. So obviously there are some curves and things which it is easier than others, namely super singular curves and anomalous curves and everything, which are just curves with like special properties. But if we're talking about general, none of those special curves, just ordinary elliptic curves over a field, and there's some like specified standards and things which say this is a safe curve to use or whatever by big corporations and things like NIST, then those curves, it's pretty hard to find, like to solve the discrete log problem. So that's just a like very mathematical problem. There's no cryptography involved yet. We're just saying like this problem in maths is hard to solve. No one knows how to efficiently compute x given just q and p. So we take this in cryptography, this hard problem, and we somehow base cryptographic schemes on this hard problem and say, if you can break the scheme, then you can solve this hard problem. Because then any break of the scheme implies that this hard problem has been solved in maths as well. So it's like a fairly safe assumption if this problem's been around for a long time and no one solved it. So yeah, a quick aside on bits of work if we're talking about security and things. So basically, if we say something has n-bit security, then we just mean that solving it would take 2 to the n operations. So for example, RSA with a 3072-bit modulus n, most standards would say that has about 128-bit security. So breaking, like factoring n or breaking RSA based on this modulus n would take about 2 to the 128 operations, which is like a really big number. And so I think that's still the current recommendation. The minimum size of n should be this large, and if n was smaller than that, then obviously the security is weaker and it could be broken. So that's what that means. So the security obviously is a lot lower than the size of n here, and that's one of the things we'll see is a lot nicer about elliptic curves than RSA, because the numbers here have to be really large to just get this 128-bit operation, like 3072-bit number n here. Whereas with elliptic curves, if we're talking about this elliptic curve discrete logarithm problem, the best attacks known for this in general run in O of square root n time. Hopefully everyone's familiar with the complexity of algorithms and things as well. So some of them are like baby step, giant step algorithm, Pollard's row algorithm. All of those kind of best algorithms known at the moment run in this time proportional to the square root of n, which is the size of the field. No, the size of the group. So if we have a field size of 256 bits, then it has security about 128 bits. Roughly half the number of bits, right? Because it's square root and this is a power. So for the same security, 128 bits of security, elliptic curves use only numbers that are up to 256 bits long, not 3072 bits long. So that's already 12 times smaller. So that's one of the main reasons why elliptic curves, well, that and number of other efficiency improvements is why elliptic curves are pretty like popular now in practice, just efficiently. It's not really anything to do with the fact that they're curves and that they're like any of that theory. They're just a really efficient group to use. So yeah, now we'll quickly come to some actual schemes which are based on this group, so that we can see kind of how they're used in practice. So this is where the actual cryptography starts, I guess. Yeah, well, is everyone okay up to this point? Any questions or anything that anyone wants to ask? Everyone's all good?
Seems good.
Yeah, so am I going too slowly or too quickly, or should be okay? No one's saying anything, that's fine. All right. Yeah, so the first one we'll look at is this key exchange protocol known as Diffie-Hellman. So this has been around for quite a while, and it's kind of the start of public key cryptography, I guess, this paper by Diffie and Hellman. But basically it's this protocol where two people on the internet, or not even on the internet, but let's just talk about the internet for now, can communicate and somehow both work out a shared secret that they both know, we'll call it K, but which anyone that was like reading all of the communication between them still can't work out. So somehow they've been able to send each other some messages and both agree on a secret value that they didn't know beforehand, but which, yeah, only they can work out and no one else eavesdropping can. So that's quite a cool idea that that's even possible. And it's really important for how the internet works, right? Because if you connect to Facebook using your laptop or whatever, then your laptop and Facebook servers have never communicated with each other before, maybe. And they still want to encrypt all the communication between the laptop and the server. So how do they encrypt things if they both don't know the same shared key that they can both use? So that's where a protocol like this would come in, is that they can send messages back and forth and somehow agree on a key which they both know, but which no one else on the internet that was watching their unencrypted communication can work out. So yeah, Diffie-Hellman is like one of the, I guess the two biggest ways to do this probably. And yeah, it works with, originally, like the original paper, works in this multiplicative group of integers modulo p prime. So you would have this group, p would be fixed, like everyone would know the same group, otherwise obviously it wouldn't work. And you would also define publicly a generator of the group, G. And then both Alice and Bob would choose a secret integer A and B, so Alice is A and Bob's B obviously, and would compute G to the power of that secret integer modulo the prime P. And then they would exchange this big A here, or the big B. So if you see here, this is actually the same as the discrete log problem that we saw earlier, but not on elliptic curves. This is just a general group. Because if you're given big A and you know the little g, the generator, because that's public, and you know P obviously because that's the group, how can you find the little a? Because you're kind of taking the log of big A with respect, like with the base G to get A. So that's the discrete log problem again. And it's also hard not on elliptic curves. So just working in the multiplicative group of integers. Yeah, so that would kind of be their secret key is this little a, and the big A or the big B is their public key in this situation. And then they would, yeah, send those big numbers to each other. So they're both visible to the eavesdropper. And then they could each compute the opposite power. So Alice will receive the capital B from Bob and raise that to her secret again. And then obviously both of them should be equal to G to the power of AB. So they'll both work out G to the AB, which they can use as their secret key. But any eavesdropper that's watched their communication and seen capital A and capital B can't use that information to work out G to the AB. There's no known way efficiently for someone to somehow combine A and B to get G to the AB. Obviously, you can like multiply them together and get G to the A plus B or something, but not to get this multiple. So that's their shared secret. And to the best of anyone's knowledge currently, this is still a hard problem to break without a quantum computer. So yeah, that's Diffie-Hellman in normal integers. And then you'll see basically the elliptic curve version is just a trivial adaptation of this. So yeah, you just define everything like you've got your field, you've got a curve, you define a public generator point again of the curve. So it's just a point on the curve, obviously not the identity. Then both of them, so that's the same as what's up here, right? You've got little g, here we've got big G. We just use capital letters to refer to points and lowercase letters to refer to field elements. And then they both again choose integers A and B and exchange their public keys. So here, instead of the power, we write the curve operations in like additive notation. And so this is just that scalar multiplication we saw earlier, this repeated point addition. So G plus G plus G plus G A times. And that gives you capital A, which is another point on the curve. And B does the same, and you swap them, and then obviously this all commutes nicely, and they can again work out this shared point AB times G, while an attacker again shouldn't be able to do that. Like if you're given this and this, there's no known way to take these two and somehow get this out of it if you don't already know A or B. So you'll note that obviously solving the elliptic curve discrete logarithm problem would break this. If you could get little a out of this or little b out of this, then you could obviously do this. But it's just one thing to know is that it's not exactly that. There's not a strict reduction to that problem. Here, the problem is not exactly the elliptic curve discrete log problem. There's this more general problem called the elliptic curve Diffie-Hellman problem, which just is basically exactly this. Given A and B, compute this. But yeah, that's not important. That's how it works. And the idea is, yeah, that Eve can't compute the shared secret key while they both can. And the reason we use elliptic curves here, like I mentioned earlier, is that compared to the size of the numbers that you would need to use for security in the kind of normal classical integer case, down here, the field size might be 256 bits or something. So these numbers A and B can be a lot smaller than they were up here. And there's nice algorithms for computing this repeated group law, not just doing it naively and drawing lines and everything, but there's nice ways to do this efficiently. So this becomes a lot more efficient, both in terms of like calculation speed and size of the numbers than the classical way of doing it. So that's really where the elliptic curves are important. Does that make sense? Yeah. So yeah, that's Diffie-Hellman, that's key exchange, which is like a nice little example, but it's not like super complicated. So I'll now show you an example of a little bit more complicated scheme, which is a signature scheme. But this still is like a very nice, elegant, simple scheme. I just like signature schemes a bit better because this is what I was mainly interested in my research. So yeah, this one's called the Schnorr signature because it was created by Schnorr, and it's really like elegant and it works in like any group. It doesn't have to be an elliptic curve, but again, for the same reason as earlier, elliptic curves turn out to be nice and efficient. So that's why this is used with elliptic curves in cryptography. So I'll quickly go through how this works as well. So again, you fix a curve E over some field FQ, and this, I can't remember if this is actually correct or if we're talking about the cyclic subgroup that's generated by G. Should have order N. Anyway, just assume that this is the group, and we've got a generator point G, which generates either the full group of points or some cyclic subgroup of it. And then, yeah, so this should be the cyclic subgroup generated by G, not necessarily the whole curve, but anyway. Then again, you would choose a secret key, which is just a integer that's smaller than n, and set your public key to this, which is repeated addition of G by itself x times. So your public key is y, and you would make that public or whatever so that you can prove that signatures that come from you are actually from you. So that's kind of outside of the scope of the problem. How do you like officially publish your public key so that people believe it's actually from you? But just assume that you have, and that somehow everyone knows that y is my public key, and only I know x, which is my secret key. And so the secret key x lets me sign a message, make a signature, whereas the public key y lets other people check that the signature I'm published is actually from me. It actually came from the public key y here. So how that works is that you would have a message and you want to sign it. So the user, me in this case, each time I sign a new message, I'll choose a new temporary secret key K. So I've actually got two secret keys here, X and K. X is the one I keep all the time, and K is just used this once. Then again, I'd do the same thing with the little K, and I'd calculate a public key corresponding to it, R. So this is again kind of like a temporary, ephemeral, that's what it means, public key. Just use this one signing attempt. And this is where we use the hash function from earlier. We'll hash this message M with this new public key R. We'll actually just use the X coordinate of it, just for simplicity, because that's what this notation means here. So we'll hash those together. This double line just means concatenation. So it's not really important how they both get fed into the hash function, but you could, for example, just literally join the two numbers together. Or if you treat them as strings, two strings together, one after the other, and feed them into the hash function, and we'll get some number out, some fixed size number. So this might be 256 bits or whatever. And then that kind of binds the message and this temporary public key here into the signature. And then we just basically work out this equation here, that our temporary secret key K minus our fixed secret key X times this hash, and obviously work modulo N, and we get S out, and S together with E is our signature, this pair of numbers. Then to verify that, if I put this on the internet or whatever along with the message, then it's pretty easy for someone to verify it. They just work out this equation here. So S times the generator point plus E times the public key, my public key, we'll give them a point on the curve, Q. That should be the, oh no, that's right. And then we do the same sort of hash here with QX and just check that the output is the same. So do you want me to go through why that works? Like just quickly write it out, or is everyone have everyone seen this before, or can everyone see why that works just off the bat? This is really hard without like an audience. I'll quickly write it out just in case. Yeah, so if we work out S times G, sorry, I'm using my mouse to write, plus E times Y, then this is going to be, the S gets replaced with this here, K minus XE.
Sam, you need to capture a different application because we can only see the PDF.
Oh, right. Yeah. Okay. How do I do that? New share. This one.
Yeah.
Yeah.
Oh my God.
Oh, now is that the screen? Hold on. Maybe this one. Ignore the the paint writing. Yeah. So we've got S times G plus E times Y. So we'll replace S with this equation K minus XE from here. And we replace the EY with E times our secret key X times G, because that's the definition of Y. And now you should be able to see that this minus XEG and this plus EXG cancel out, and you just get K times G, which should equal R. Let me just switch back to the PDF. Yeah, so that should equal this R, this K times G. So Q should equal R if the signature is valid. And then when we compute the hash again, which is QX concatenated with M, then this should be just RX concatenated with M. So this E should match this EV. And that's why this all checks out. And obviously if something was not right, then Q would not be equal to R and the hash would not add up and it would just not work. It would not verify. So yeah, that's kind of like a pretty elegant signature scheme where you can prove that the signature on this message came from this public key. And if you change the message, then the hash won't add up. And if you change this public key, then it obviously won't work. And everything just kind of relies on each other. So it's a proof that whoever owns this secret key and this public key actually generated this signature on this message. So for those of you that haven't seen signature schemes and stuff before, this is like super useful in the real world for things like authenticity of computer, like updates on a computer. If you receive an update from Microsoft, how can you actually verify it came from Microsoft? Or if you're sending like an important document across email to someone, how can you actually kind of sign it, really sign it, not just write a hand signature and upload that as a scanned PDF or something? Because everyone knows that it's pretty easy to copy a signature out of a PDF and put it on another one or whatever. Like with the computer, that's trivial. So this whole kind of digital signature idea replaces that old way of doing things. And as long as you can somehow guarantee that the public key is actually right, like the public key you've got is actually my public key, not an imposter, then the signature, if it checks out, should always be valid. So yeah, that's and the cool thing about this specific scheme is that there's a proof that it actually does rely on the discrete logarithm problem. If somehow you can make a forged signature from this scheme, then you can always break the discrete log problem. So because we assume that it's hard and that no one knows how to break it, we can kind of assume that this scheme is pretty secure. And that's not like entirely obvious if you're just looking at it, right? If you just look at this equation and you can think, is there some way that I could play around with the numbers and the curve point and everything and somehow work out what x is or what k is or something, or like if I'm calculating this stuff in here, then I've worked out what r is. Does that tell me anything extra? Like, well, there's a few moving parts, and this is quite a basic example. So some of the more intense examples are even worse. But like, if you've got this security proof here, then it kind of just does give a bit more confidence to the whole thing that says, yeah, like if you can make a forgery, then you do break this hard problem. So even with all the moving parts, hopefully, if the proof is right, of course, we know that it is provably secure. So yeah, that's like one of the nice things about this. The problem with this scheme was that it was patented for like 20 years, so it wasn't standardized or anything properly. But now the patent's expired, so it's becoming more popular again because people are allowed to use it like properly, legally. Yeah. Okay. So is that all clear? Everyone happy with the two examples of elliptic curve cryptography that I showed you?
Yep.
Yeah. Cool. So yeah, I'll just quickly talk about some hyperelliptic curves now then, as a bit of a generalization. And this will be a bit more mathematical for hopefully the people that are bored out of their minds by the really basic elliptic curve stuff. So yeah, and a hyperelliptic curve is just the same as an elliptic curve, but it has a higher genus. So the other conditions, like the fact that it has to be non-singular and everything, are all the same. Sorry. But yeah, it has a higher genus, so like genus 2 or 3 or something like that. And it has an equation of this form, so like in general. So it's the same as the elliptic curve equation, right? You've got y squared. If we assume hx equals 0, which is allowed to be, then this is just y squared equals some function of x. And if this function of x was a cubic, then you'd get an elliptic curve, because genus 1 gives you degree 3, right? But if this polynomial has like degree 5, then you get a genus 2 hyperelliptic curve, not just an elliptic curve. So we'll just assume hx equals 0 here for simplicity. But yeah, in general, this can actually be 2g plus 2 as well, I think. But yeah, we'll just stick with the simpler case. So we have a curve like that, and a field that we define the curve over, we'll call it k. So again, we can look at the set of k rational points on that curve in the same way that we were looking at the points on the elliptic curve that have coordinates in fq. So obviously points are an x and a y value, both are in k, that are on the curve. And we also include the projective point at infinity, that I've written as infinity. Sometimes you'll see this written as like a mathcal O, but I'll call it infinity here. So yeah, and then unlike genus 1 curves, so unlike elliptic curves, these points don't make a group. Because if you remember when I was talking about the elliptic curves, I said that the kind of deep algebraic geometry behind it, the fact that there's a group law, is that it's isomorphic to its Jacobian, which does have a group law. Whereas here, it's not. That's not like a general fact. So in genus 2 and above, that's not true. And so the group law is going to look a lot more complicated. But we can still get a group out of these points somehow by using the Jacobian. Don't worry if you don't know what a Jacobian is or anything. Like, it's not too important what the details are, but I just want to show a little bit of the theory behind it to give people an idea of where higher like generalizations of elliptic curves can come into cryptography. So yeah, we'll define quickly some things which might look a little bit scary at first, but hopefully if you haven't seen them before, they're not too complicated. So yeah, I'll call a divisor is just this formal sum of points. So it's not a sum of points. We're not adding the points up like we did with the group law, because remember there's no group law yet on the points. So we just write the square brackets around the point to show that we're kind of just treating it as a symbol. It's just a symbol where we have like some points and they've all got a coefficient, and there's only finitely many of the points here which have non-zero coefficient. So it's just a finite sum of these formal symbols which represent the points. So all of these divisors, all of these formal sums of points like this, form a group, it turns out. And we'll talk about the degree of divisor as just the sum of these coefficients. And so it turns out that the divisors of these whose coefficients all sum to 0, so some will be negative and some will be positive, but they all sum to 0. These degree 0 divisors is a proper subgroup of all of the divisors. And then we'll make another definition, which is called a principal divisor. And these are special divisors. So they're still formal sums of points, but we put a special condition on the coefficients of these points. And we say that the coefficient is the order of a 0 or a pole at that point of some function, gamma. So yeah, hopefully everyone knows what a 0 or a pole is of a function if you've done analysis and things. But if you've got a divisor which you can generate from this function, like you take a function gamma, a rational function on the curve, which, yeah, you can just think of it as a quotient of polynomials, f over g. And anywhere that it has a 0, you would write the order of that 0 times the point that gives you that 0. And anywhere that it's got a pole, you would write negative of the order of that pole times the point that gives you the pole. And it turns out that all of the principal divisors of this form, from rational functions, they all have degree 0, and they're actually a subgroup of the divisors of degree 0 on the curve. So that's like really non-obvious, and apologies that I'm really brushing over the details here, but that's the main idea. You've got this special set of divisors that come from functions inside the general set of divisors, which are just these formal sums of points. And because of that, you can define the quotient group here of degree 0 divisors, quotient by the principal divisors, the special ones that come from functions. And this group here is it's known as the divisor class group, but you can also kind of call it the Picard group or the Jacobian, which are not like exactly the same definition as each other, but they're all kind of isomorphic as a group. So I'll just use those terms synonymously here. And so, yeah, basically this just means that if you have two divisors of degree 0, then if their difference is a principal divisor, if their difference as divisors is one of the form of this, then they are the same. So it's just an equivalence relation. It's just how the group's defined. And for each equivalence class, there does exist a special unique representative called a reduced divisor. So we can use those for representing the equivalence classes and for computation. And the group law is kind of complicated, and so is the representation as two polynomials. So I won't go into any of that detail here. But if you are interested, it's all like accessible. There's a really good book that I've got in the references here as well, which you can have a look at if you're interested in learning a bit more about this kind of stuff. But yeah, time's going on, so I won't go into that in here. But yeah, we've got this group now of degree 0 divisors, quotient by the principal divisors, and a group law called Cantor's algorithm. And this now is a group, but it's not isomorphic to this set of points. And actually what it does kind of look like is that it's really pairs of points. And for pairs of points, you get a group law where you have like a function going through the first pair, and the second pair gives you a function through the third pair of points, which then reflected would be the sum. So you can kind of see the parallel between this and the elliptic curve stuff, right? If this was an elliptic curve, then the group law would be a straight line through 2 points and then a third. Whereas here we've got a cubic which goes through 2 pairs of points through a third pair of points. And that's in genus 2, sorry. So you can kind of see how it generalizes, but obviously that's quite a lot more complicated than the one we saw earlier. And this diagram comes from this paper here, just for credit. So the problem is that the group law here actually gets weaker and weaker to attacks on the DLP as the genus increases. So beyond, even genus 3 is not considered like entirely safe, just because the discrete logarithm problem becomes easier than on genus 2 and on elliptic curves by index calculus attacks. But with genus 2, it is still like considered safe from index calculus attacks. So you can get a group from the points on a genus 2 hyperelliptic curve. And that's kind of what my recent paper on groups of unknown order uses. It uses these groups from genus 2 and 3, from hyperelliptic curves, the Jacobians, the group law. So there are cryptographic applications of that too, and I won't get into my paper either, but that's what I've been working on. So that's why I thought I'd mention that too here as well. Like I said, if you just think about this Jacobian here, the isomorphism with an elliptic curve is pretty simple. If you've got a point on the elliptic curve, you send it to a divisor of this form. Just that point minus the point at infinity. So remember that the coefficients have to add up to 0 because this is the degree 0 divisor. So that's why that has this minus infinity here. But yeah, that's like the isomorphism. And so if you think about the group law Cantor's algorithm on this group of divisors like that, that gives you exactly the chord tangent rule that we saw on the curve through that isomorphism. So it all does work out nicely. And then isogeny-based cryptography is also very elliptic curvy. Isogenies are maps between elliptic curves, and I'm not going to talk about that at all today because I see Tristan's got it on the list for later. So just so you know, there's a whole area of cryptography which utilizes isogenies between elliptic curves instead of points on elliptic curves in the group law there. But yeah, I'll leave that for Tristan. So that's all that I wanted to talk about today, and the timing seems to have worked out nicely, but hopefully that wasn't too fast or slow or repetitive or anything. And here's some quick references. This first one's a very good book on elliptic curves and cryptography if you're interested in getting started. And this Handbook of Elliptic and Hyperelliptic Curve Cryptography by Cohen and Frey, I don't know whether Anne's one, is like very good book, very massive book if you want to get started with hyperelliptic curves as well. But yeah, that's all from me. So hopefully that's been somewhat interesting or beneficial or whatever in some way. So yeah, thank you for listening.
Samuel, I have a question.
Yeah?
Like you were talking about this Schnorr signature.
Yeah.
Can you move to that part?
Yeah.
So there's this permanent key they have, and like the protocol is using some other ephemeral key. So when like it's assuming that this problem is hard and there is a permanent key, what is the requirement of this ephemeral key? I mean, this is the whole thing, introducing this thing. I mean, we already have a key.
So what's the point of it, or what's the security?
No, I mean, well, why do we need to, what is the requirement of introducing this ephemeral set of keys when we already have a permanent set of public key for this signature thing? Yeah,
so basically it's to hide the permanent key because this one changes every time. And if you think about this number here, if we didn't have k, then x times e is pretty easy to like invert e and find x, right? So k basically just makes s a random element of the group because k is big enough that k minus x times e mod n could be anywhere within modulo n, like anywhere within this cyclic group. So because this changes every time, and if this doesn't change every time, if you use the same k twice on different messages, you can break it. You can find the secret key. So it's really important that k does change each time. But yeah, that's what it's there for, is to hide the secret key, to hide what minus x times e is.
Okay, okay, got it.
Any other questions for you?
Just in general, like, why are elliptic curves, like, they seem to come up absolutely everywhere? Is there like a reason for it?
Well, yeah, like in cryptography, like I said, it's because of their efficiency, but I guess they're pretty mathematically nice for a lot of properties, like the fact that they, I don't know, like the rational points are finitely generated, and yeah, you get this nice group law and everything. So there are abelian varieties, quite like simple examples of abelian varieties. I don't know, maybe Lucas has some more deep insight, but
Right.
yeah, I don't know, it's kind of historical as well, I guess, because they not just these, but like Diophantine equations or whatever in general, like people have always been interested in their solutions for like thousands of years, isn't it? So
It's just the first non-trivial thing next to the projective line, right? And everything that's half high degree gets harder. So that's why everyone is into elliptic curves. In terms of Diophantine geometry.
yeah.
Right.
Because, yeah, I mean, even for higher genus abelian varieties, I mean, you have lots of properties that are even maybe harder, or if things go wrong, or
Yeah, like already with genus 2, this group law is a lot more complicated, and like representing the elements and everything is a lot more complicated, because points on the curve are obviously pretty easily represented as just the 2 coordinates, or in fact actually you really only need 1 coordinate and 1 bit, because for every x coordinate there is only 2 possible y coordinates, the negative and the positive one. Or you can represent it as the odd one and the even one, or you can represent it as the one which is a quadratic residue and which one isn't. Like there's heaps of different ways that you can differentiate the two, but basically you only need 1 bit of information to differentiate the two, and then you can just represent it as one integer, the x coordinate, whereas here you've got like a representation as 2 polynomials, and you can compress this as well a bit, but it's still a lot more of a complicated representation, and the algorithm's a lot more complicated.
Yeah, I think what you have to realize is that the Jacobian itself is another variety, and even writing down a group law in that thing generically, I mean, it takes lots of equations and whatnot. So this is really somehow the best and easiest representation you get. And this is just hyperelliptic curves, right? So if you have a Jacobian that doesn't come from a hyperelliptic curve set, it's even harder to do anything there.
Yeah, when I say Jacobian here, I'm just talking about it as a group, if that's confusing for anyone. This Jacobian is a lot like more complicated than just a group, but yeah, it's just for simplicity. Any other questions? Anything that anyone wants me to go back to or anything?
Why is a coordinate an elliptic curve?
Yeah, it's nothing to do with ellipses.
Because of elliptic functions.
Well, I don't. Yeah, I can't remember.
Yeah, it's because of historically, it's because of elliptic functions. I mean, if you look at elliptic integrals that give you elliptic functions, then the denominator of these elliptic integrals are exactly the right side of an elliptic curve, for example, and that's why it's called elliptic curve.
There we go. Thank you, Lucas.
Right. Thanks.